Now, we all notice that the sun rises and sets every day. But have you ever wondered why its path across the sky is not the same throughout the year? So, in this section, we will uncover the annual motion of the sun, what causes the seasons, and the fascinating motions of the planets that puzzles astronomers for centuries. First, let's clear up a pair of words we often mix up: rotation and revolution. So, in astronomy, they mean two different things, and both explain key parts of how we experience time here on Earth. Have you ever watched the sky change from day to night? That's thanks to Earth rotating. One full spin takes 24 hours, and that's why we experience day and night. Now, Earth also revolves, meaning it moves in a big circle around the sun, and one full revolution takes 1 year. So, while rotation gives us days, revolution gives us seasons and the calendar year. So, don't mix up these terms. Here's a quick way to remember it. Rotation is like a basketball spinning on your finger, and revolution is like that basketball moving in a circle around your head. Now, have you seen international news where it's morning for you but dark in another country? That's because different parts of Earth face the sun at different times, and rotation causes that. So, this diagram shows people at different spots on Earth. Each one sees a different part of the sky because of rotation. So, rotation brings us sunrise and sunset, and revolution gives us the year. Easy to confuse, but now you have got this. Let's keep exploring how these motions affect the sky we see. First, let's talk about a common misunderstanding. Why we don't see stars during the daytime? Are they gone? Or is something else is happening? Imagine the sky is full of stars all the time. So the reason we can't see them during the day is because the sun lights up our sky and overwhelms their faint light. So the particles in the atmosphere scatter sunlight in all directions, filling the sky with brightness. So if the sun were not so bright, you would actually see it moving with a starry background, just like the moon at night. It will rise next to a constellation, drift across the sky, and set with those same stars. So even though it looks like the sun is just rising and setting, if you could watch it against the stars, it would actually be creeping eastward slowly, one day at a time. It shifts about its own width. So that's about one solar diameter due to Earth's motion. So does anyone remember how many degrees the whole sky spans? It's 360 degrees. The sun moves about 1 degree a day. So this slow eastward shift means the sun aligns with different constellations throughout the year, leading to seasonal change. We will talk about it more in next slides. So even though we can't see stars, the sun is making its way across a background of stars every day, changing with constellations lie behind it. Now that we know the sun moves against the stars, let's talk about the path it takes and what that means for what we see in the sky. So we say that the sun is in Sagittarius or Aquarius, not because it's next to them, but because from our view, it lines up with those stars in the background. So the sun is not close to them, just aligned that way. So the sun appears to move through the background stars, and his path is called the ecliptic, and it's the projection of Earth's orbit onto the sky. Think of the ecliptic like Earth's shadow trail on the sky, where the sun appears to travel over time. It's not random. Is tied to our orbit around the sun. So the sun loops once around the whole sky in about 365 days, moving 1 degree per day. That might seem small, but it adds up to big changes like the seasons. But you don't notice the shift day to day. But over weeks, the sun rises and sets in new positions, hitting different parts of Earth more or less. And that's how we get seasons. So as a summary, let's pay our attention to this image. Earth moves around the sun in a nearly perfect circle, but when we look at the diagrams, the orbit even looks like an oval because of the tilted view. As Earth orbits the sun appears to move slowly across the background of stars. If we could see stars during the day, we would notice the sun passing in front of different groups of stars or constellations. And this path that the sun seems to follow through the stars is called the ecliptic, and it shows us the shape of Earth's orbit in the sky. Now let's clear up one of the biggest myths about season. Earth is not hotter in the summer because it's closer to the sun. Let's find out what really causes seasons. Imagine if Earth stood straight up, not tilt. Then we would have no real summer or winter. It's the tilt that gives us seasons. Most people think we have summer because we are closer to the sun. But nope. The real reason is that Earth is tilted like a leaning, spinning top. And that tilt means different parts of the planet faces the sun more directly at different times of year. So if the Earth were not tilted, what seasons would it be all year long? What do you think? Something like spring or fall, mild and consistent everywhere. And because of Earth's tilt, the sun doesn't stay in the same place in our sky. So in summer, it rises higher and stays longer. More daylight, more heat. But in winter, it stays low and we get shorter, colder days. So these four key points divide the year into seasons. They have been tracked for thousands of years. People held festivals, built monuments, and even planned farming around them. So in summary, it takes our Earth 365 days to revolve or orbit around the sun. And during some part of the year, the top half of the Earth, where the National Air and Space Museum is located in the northern hemisphere. So that part is tilted away from the sun, while the bottom half is tilted toward the sun. And 6 months later, the top half of the Earth is tilted toward the sun, while the bottom half is tilted away from the sun. And when the northern hemisphere is tilted away from the sun, it is winter there. Less sunlight is hitting the northern hemisphere, making the days shorter. And at the same time, it is summer in the southern hemisphere. And 6 months later, after the Earth travels halfway around the sun, the top of the Earth is tilted towards the sun, making it summer there. More sunlight is hitting the northern hemisphere, making the days longer. And at the same time, it is winter in the southern hemisphere. Now that we know why Earth has seasons, let's dig deeper. What doesn't cause the seasons? And how have people connected to these seasonal changes throughout history? Right now, it might be blazing hot in Texas. But in places like Argentina or Australia, it's winter. That's because when the northern hemisphere tilts towards the sun, the southern tilts away. Can anyone guess what month Australians celebrate Christmas in? December? But it's summer there, not winter. So here's a common myth that summer happens when Earth is closer to the sun. But surprise, Earth is actually closest to the sun in January. So why is it cold there? Because we are tilted away. So next time someone says it's hot because we are closer to the sun, you can tell them, actually we are closer to the sun in January. And now we know that the seasons depend on the angle of the earth to the sun, not how close to earth is to the sun. More concentrated sunlight shines on the part of the earth tilted towards the sun, and less concentrated light shines on the part of the earth tilted away from the sun. And long before clocks or calendars, people watched the sky. They knew when the days got longer or shorter and celebrated the changes with dances, storytelling, even architecture. Some cultures marked midsummer with giant feasts, others saw winter solstice as a time of renewal. So, next time the seasons change, remember it's not just science, it's part of our culture, history, and even some fun science myths. So, we see stars twinkling at night. But did you know some of the brightest objects in the night sky are not stars at all? They are planets. Let's explore how they move and how we can spot them. Unlike stars which generate their own light, planets simply reflect sunlight. That means when we see Jupiter or Mars glowing in the sky, it's like looking at a tiny sunlit mirror from millions of miles away. Have you ever spotted a really bright star after sunset? That was probably Venus. It's often the first object to appear. Now let's picture the solar system like a racetrack. All the planets circle in the same direction, counterclockwise if you are floating about the North Pole. But not all the lanes are the same. Planets like Saturn take a long time to finish a lap because they are so far from the Sun. Any guesses which planet is the slowest spoke? Saturn takes almost 30 years to orbit, while Earth takes only 1 year. So the ancient Greeks noticed some stars didn't stay put. They drifted slowly across the sky night by night. So they called them planets, which means wanderers. And they really do wander. Mars makes a full loop in about 2 years, while Saturn strolls slowly through the stars. Next time you're outside, try to spot something that glows but doesn't twinkle. That's likely a planet. So we have learned that planets move in orderly paths, reflect sunlight, and slowly drift among the stars. Now let's focus on two that are hard to spot, Venus and Mercury, and how ancient cultures connect them to myths. So these two never wander far from the sun in our sky. That's why we don't see them high overhead. They are low and quick, often hiding in sunlight or haze. Mercury is especially hard. It hugs the sun so closely that spotting it takes perfectly timing and a clear horizon. This figure shows that Mercury and Venus follow orbits that keeps them near the sun, and they are visible only soon after sunset or before sunrise, when the brilliant sun is hidden below the horizon. So have you ever seen something really bright near the sunset? That was probably Venus. It's the showstopper of the evening sky. Even though they are not stars, ancient people called Venus and Mercury morning or evening stars. Venus especially can shine so brightly it can cast shadows. That's why poets and sailors kept a close eye on it. It was their celestial timekeeper. And Venus takes 584 days to move from the morning sky to the evening sky and back again. But Mercury zips around in only 116 days. Now here's a fun fact. Venus is so bright. It's the second brightest object in the night sky, right after the moon. Now thousands of years ago, people noticed that planets followed a consistent path, the ecliptic, and they gave meaning to the constellations they passed through. That became the zodiac. Today, astronomy is based on evidence and math, while astrology is more symbolic and cultural. Anyone know their zodiac sign? It's fun to explore, but remember, it's not based on science. Even though planets don't shape our future, their movements inspired storytelling. So ancient people watched the sky closely, and so can we. Now let's talk about something much bigger than just seasons. Massive climate changes that happen over tens of thousands of years. Do you know that the Earth's movement is not fixed? It goes through subtle, slow changes. So the shape of its orbit becomes more or less circular, which we call eccentricity. And the direction of its axis shifts, which is the precession. And next, the angle of its tilt can also change, which we call as the inclination. So these tiny motions happen over tens of thousands of years, but together they can change Earth's climate. So these astronomical cycles affect how much sunlight reaches certain parts of the Earth, especially the poles. Less sunlight means colder climates. And over time, that can trigger massive glaciation and ice ages. So while these changes are slow, they pack a punch over long periods. So believe it or not, we are still in an ice age. We are just in a temporary warm phase. And there's still ice at the poles. That's why scientists say the current ice age is still ongoing. Did anyone think that the ice age was completely over? So these natural cycles work slowly, but they shape Earth's climate over thousands of years. And they remind us that Earth's environment is always changing, even if we don't notice it right away. So let's meet the man who cracked the code behind Earth's ice ages, long before anyone believed him. Milutin Milankovic, an engineer and mathematician from Serbia. Back in the 1920s, he had a big idea. What if Earth's changing path through space could explain climate patterns, even ice ages? So he proposed that three slow changes in Earth's motion: the shape of our orbit, the tilt of Earth's axis, and the wobble in that axis, all combine over time to change how much sunlight Earth gets. So this became known as Milankovitch hypothesis. So when Earth's orbit is more circular and the tilt is smaller, some places don't get enough summer heat to melt winter snow. So year after year, the snow builds up and boom, you start getting glaciers again. So it took decades, but scientists finally looked deeper into the ocean floor. So they found fossil layers showing temperature swings that lined up almost perfectly with Milankovitch's predictions. That's when the scientific community started taking his theory seriously. Isn't it amazing that the ancient shells in the ocean proved his theory? So this image shows a graph of fossil temperature records over time with calculated solar heating. So this is the most relevant visual evidence supporting the hypothesis. So Milankovitch shows us that tiny shifts in space can cause massive changes on Earth, and that sometimes it takes decades for science to catch up with the bold ideas. Now that we know what Milankovitch proposed, the next big question is, how do we know it's actually true? Let's look at how scientists gathered evidence to support or challenge his idea. I explained a little bit about it in the previous slide. Now let's dig deep. So in 1970s, scientists drilled into the ocean floor and found a long-term climate record that lined up beautifully with what Milankovitch predicted. So these sediments held the temperature history of Earth's oceans, as we saw in the temperature graph in the previous slide. But science doesn't always give neat answers. In the 1980s, another team found evidence from a cave in Nevada called Devil's Hole. That seems to show warming happened too early to match Milankovitch cycles. Was one of them wrong? Turns out neither. In 1997, researchers found that Devil's Hall was recording local climate, not the global picture. Meanwhile, the ocean data still matched global Milankovitch predictions. So this is a great example of how science works. Not by being perfect from the start, but by improving as new evidence appears. Contradictions aren't failures. They help sharpen our understanding. So what do you think? If you found data that didn't match a popular theory, what would you do? That's the heart of science. Keep asking, testing and learning. So with this slide, we are going to conclude the chapter 2. Now let's see the summary. So let's take a moment to review the key ideas from this chapter. So in the first section, we explored how the sky is divided into 88 official constellations, many with roots in ancient mythology but named in Latin. Some familiar patterns like the Big Dipper are not full constellations. They are called asterisks. And stars named using Greek letter and their constellation name, usually ranked by brightness. We also learned how astronomers measure star brightness with the magnitude scale. Remember, a lower number means a brighter star. Finally, flux helps us understand how much light energy we receive from each star. And in the second section, we introduce the concept of the celestial sphere, a way to visualize the sky with the earth at the center. And the sky appears to spin around us because of Earth's rotation. So we identified key points like the celestial poles, equator, zenith and nadir. So sky distance are measured in angles, not in kilometers or miles. And that's why we use angular units like degrees, arc minutes and arc seconds. An important point here is that your latitude tells us how high the north celestial pole appears in your sky. Lastly, we learn about precession, a slow wobble of Earth's axis caused by the Sun and Moon's gravity. And it takes about 26,000 years to complete one cycle. Next, the section 3 covered the motions of Earth and how they relate to what we see in the sky. So Earth's rotation causes day and night, while its orbit around the Sun gives us the seasons. And the Sun follows a path called the ecliptic, and it appears to move through the constellations during the year. So because of Earth's axis is tilted, we have changing seasons, not because of how close we are to the Sun. So the start of each season is marked by an equinox or solstice. So we also talked about how planets travel along the ecliptic and can be seen as morning stars or evening stars depending on when they are visible. So in this final section, we introduce the Milankovitch hypothesis, which explains how long-term changes in Earth's orbit can affect climate and even cause ice ages. Now there are 3 key cycles, remember? Eccentricity, that means how stretched out Earth's orbit is, which changes every 100,000 years. And next, tilt, that means the angle of Earth's axis, which changes over 41,000 of years. And next, precession, the wobble of Earth's axis, which takes 26,000 years. So together, these cycles influence how much sunlight reaches Earth over time. And scientists have found strong evidence for this in ocean sediments and ice cores. That's why the hypothesis is now widely accepted. Now that's the end of chapter 2. So these ideas help us connect everyday observations to big scientific principles. So please go through the practice questions and try to solve them by yourself first. And answers are given at the end.